So here we have a family of systems, family of linear systems with one parameter A. We're wondering, how does the behavior of the system change as A changes? That's the goal. Do big changes occur? You could call those bifurcations. The trace-determinant plane is a tool for helping us think about the bifurcations that can occur. Again, the critical loci are the t-axis, where d is 0. The positive d-axis, where t is 0 and d is positive, and what's called the repeated root parabola, which is kind of coincidence because it's also got, itself has a repeated root, but what we're talking about when I say repeated root parabola is that the eigenvalues are repeated. The equation is d equals t squared over 4, which is usually simpler to think about as 4d equals t squared. So you want to figure out the trace and determinant as functions of the parameter. I'm abusing notation here, but that's okay. Trace is the sum of the entries on the main diagonal, so that's 2a. Determinant, you can see, is a squared minus a. A times a minus 1. What you want to do to really fully understand what's going on is you want to plot this parametric curve, TD equals 2a comma a squared minus a in the trace determinant plane as a increases. You could use parametric mode in your calculator if you wanted to, parametric plot in Mathematica. Could I do it without? Yeah, I mean, I could plot points, like when a is 0, I'm going to be at the origin. When a is 1, I'll be at the point TD equals 2, 0. Right, when a is 1. Trace is 2, determinant's 0, but I'm back to the t-axis. Interesting. I mean, I could plot more points, pick more values of a. Maybe it's worth doing one more. When a is 2, TD is 4, 2. 4, 2. Somewhere over here, is it above or below this parabola? 4 times the determinant here, 4 times 2 is 8. T squared is 16. D is less than t squared over 4. We'd be below it. Plot more points. Is there a way to figure it out without just plotting a bunch of points, what it looks like? Yeah, you could realize that this equation implies a equals t over 2. And you could plug that into this equation in place of the a's to eliminate the parameter. Remember doing that in multivariable calculus, eliminating the parameter sometimes? If you do that, you get d equals t over 2 squared minus t over 2. That's 1/4 t squared minus 1/2 t. That's a parabola that you could graph and understand the graph using ordinary methods of calculus. You can also factor it like this and realize it's got t roots at t-intercepts at 0 and what would it be, 2? Yeah, I already knew that. That's a 2 there. And it's an upward opening parabola. It's going to look about like this, it seems. Will it touch the repeated root parabola over here? Boy, perhaps not. Do you see d equals t squared over 4, a 1/4 coefficient of t squared there? There's also a 1/4 coefficient of t squared there, but I'm thinking it's not going to. But if you want to be sure, you got to solve some equations. When does it cross the t-axis? That's when some bifurcation occurs. Bifurcations occurs. That's when d is 0, which is a equals 0 or a equals 1. You're at the origin when a is 0. You're at this point when a is 1. Does that conflict with the fact that t is 2? No, because t equals 2a along this curve. So the 2 corresponds to the t coordinate of that point, the trace. A equals 1 is when the parametric curve is at that point. That is a bifurcation value. Are there any other bifurcation values? Do we ever cross this positive d-axis? It doesn't seem so. T would have to be 0. That only occurs when a is 0. We only cross at the origin effectively. The origin is on the t-axis. It's still on the critical locus there. Do we ever cross over here? It seems like probably not, but to make sure, we want to take this equation and substitute in terms of a and see if we can solve for a. Are there any real solutions? A does have to be a real number here. So we get 4d, it would be 4a squared minus 4a equals t squared. That would be 2a squared. All I'm doing is I'm taking that equation and plugging in how t and d depend on a. And this is ultimately telling us that the only time it crosses the repeated root parabola is when a is 0. So the only bifurcation values are 0 and 1. If it were a curve that did cross again, you'd have to figure out when it crosses again. Should also briefly, I know we're about out of time, briefly describe the nature of the bifurcations. Don't just draw the curve, describe what goes on. When a is less than 0, you're over here. The red curve is over there. I didn't draw it over there, but it is. When a is less than 0, you're up there. That's where the origin is going to be a spiral sink. Don't call it underdamped because it's not a harmonic oscillator. Spiral sink. Down here, when a is between 0 and 1, that spiral sink somehow morphs into a saddle point. Because down here is where saddle points occur. And then when a gets bigger than 1, over here, it's a real source. So if I took the time to animate this with Mathematica, animate a stream plot, maybe you want to do that, you would see as a varies, use manipulate, you'd see it morph from a spiral sink to a saddle point to a real source. Kind of mysterious, like how would that happen? I'd encourage you to investigate. Have a good day.